Approximately 1,800 miles beneath our feet, swirling liquid iron in the Earth's outer core generates our planet's protective magnetic field. This magnetic field is invisible but is vital for life on Earth's surface because it shields the planet from solar wind, streams of radiation from the Sun. About 565 million years ago, however, the magnetic field's strength decreased to 10% of its strength today. Then, mysteriously, the field bounced back, regaining its strength just before the Cambrian explosion of multicellular life on Earth. What caused the magnetic field to bounce back? According to new research from scientists at the University of Rochester, this rejuvenation happened within a few tens of millions of years, rapid on geological timescales, and coincided with the formation of Earth's solid inner core, suggesting that the core is likely a direct cause. The inner core is tremendously important, says John Tardino, the William R. Keenan, Jr., Professor of Geophysics in the Department of Earth and Environmental Sciences and Dean of Research for Arts, Sciences Engineering at Rochester. The research provides clues about the history and future evolution of Earth and how it became a habitable planet, as well as the evolution of other planets in the Solar System. Unlocking information in ancient rocks. Earth is composed of layers: the crust, where life is situated; the mantle, Earth's thickest layer; the molten outer core; and the solid inner core, which is, in turn, composed of an outermost inner core and an innermost inner core. Earth's magnetic field is generated in its outer core, where swirling liquid iron causes electric currents, driving a phenomenon called the geodynamo that produces the magnetic field. Because of the magnetic field's relationship to Earth's core, scientists have been trying for decades to determine how Earth's magnetic field and core have changed throughout our planet's history. They cannot directly measure the magnetic field due to the location and extreme temperatures of materials in the core. Fortunately, minerals that rise to Earth's surface contain tiny magnetic particles that lock in the direction and intensity of the magnetic field at the time the minerals cool from their molten state. To better constrain the age and growth of the inner core, Tardino and his team used a CO2 laser and the lab's superconducting quantum interference device, SQUID, magnetometer to analyze feldspar crystals from the rock anorthosite. These crystals have minute magnetic needles within them that are perfect magnetic recorders, Tardino says. By studying the magnetism locked in ancient crystals, a field known as paleomagnetism, the researchers determined two new important dates in the history of the inner core. 550 million years ago, the time at which the magnetic field began to renew rapidly after a near collapse 15 million years before. 450 million years ago, the time at which the growing inner core structure changed, marking the boundary between the innermost and outermost inner core. Because we constrained the inner core's age more accurately, we could explore the fact that the present-day inner core is actually composed of two parts, Tardino says. Plate tectonic movements on Earth's surface indirectly affected the inner core, and the history of these movements is imprinted deep within Earth in the inner core structure. Avoiding a Mars-like fate, better understanding the dynamics and growth of the inner core and the magnetic field has impo. Researchers believe that Mars, for example, once had a magnetic field, but the field dissipated, leaving the planet vulnerable to solar wind and the surface ocean less. While it is unclear whether the absence of a magnetic field would have caused Earth to meet the same fate, Earth certainly would have lost much more water if Earth's magnetic field had not been regenerated, Tardino says. the planet would be much drier and very different than the planet today. In terms of planetary evolution, then, the research emphasizes the importance of a magnetic shield and a mechanism to sustain it, he says. This research really highlights the need to have something like a growing inner core that sustains a magnetic field over the entire lifetime, many billions of years, of a planet. Materials provided by University of Rochester. Original written by Lindsay Valich. Note: content may be edited for style and length. How did Earth avoid a Mars-like fate? Ancient rocks hold clues. New paleomagnetic research suggests Earth's solid inner core formed 550 million years ago and restored our planet's magnetic field. Science Daily. Ancient rocks hold clues. New paleomagnetic research suggests Earth's solid inner core formed 550 million years ago and restored our planet's magnetic field. Ancient rocks hold clues. New paleomagnetic research suggests Earth's solid inner core formed 550 million years ago and restored our planet's magnetic field. Science Daily. https://ift TT QDCLPN3 accessed July 25, 2022. Thanks for watching. Please subscribe my channel for more videos.